Hello everyone, my name is Sourya and I'll be presenting our work titled Mixing of Three-Term Progressions in Quasirandom Groups. This is a joint work with Amey, Bhangale and Prahladh Harsha. We'll start with a very popular result in theoretical computer science, which is called the expander mixing lemma. The lemma says if H is an expander graph on the vertex set V and S set E, and we take two functions f1 and f2 from the vertices to the complex numbers, both of them are bounded functions, then these two expressions are approximately equal to each other. So what we have over here, so in the right hand side, we have product of expectations of individual functions. And this expectation is computed over the uniform distributions on the vertices. On the right hand side, we are computing the expectation over the distribution UV randomly sampled from the H set E and computing the quantity F1 of U times F2 of V. Okay, and the lemma says these two quantities are roughly equal, and that is a good news because we know there are constant degree expander graphs and we know how to construct them efficiently. So let's, if we take like a expander graph on a constant degree D and consider right term and left term. So we look at the distribution. So the right hand side, we have distribution over roughly V squared number of elements. On the left hand side, we have a distribution over roughly D times V number of elements. Okay, so if D is a constant with respect to the cardinality of the set V, then D times V is way smaller compared to the cardinality of V squared. So this is a nice example of pseudo random behavior, and it has a lot of application. Now we focus on a similar question, but in a slightly different setting. So instead of taking H to be a graph, we take H to be a three uniform hypergraph. So now let's take three functions, f1, f2, and f3, and again compare terms as before. So on the right-hand side, what we have product of expectations of individual function. On the left-hand side, again, we sample U, V, and W, which is a hyper H from the H set. Then we compute f1 of U, f2 of V, times f3 of W. Okay, and we consider studying this mixing phenomena over specific hypergraphs where the vertex set is going to be a group G. What kind of hypergraphs we're talking about over here? There will be two of them, H1 and H2, where H1 will be a hypergraph on the vertex set group G, and the H set will be E1. And how E1 is defined is the set of all non-trivial triples like this, x, y, x times y, where both x, y belongs to G. And non-trivial meaning we ignore all the triples where either x or y is identity. Okay, so H1 is defined that way. H2, for H2, the vertex set is again a group G. The H set E2 is defined using a slightly different pattern. So it is the set of all non-trivial triples like this, x, x times y, x times y square. So it's the set of all non-trivial three-term progression in G. Now, one might wonder, what is exactly the motivation behind studying mixing phenomena over these hypergraphs? So let's talk about H1 first. So mixing for H1 implies that if we take any large subset A within G, that is not going to be product free. Or equivalently, take any large subset A in G, then there will be a non-trivial triple x, y, x times y, where all three of them will be in A. And to say this, why this is true, so fix any large subset A within G and take f1, f2, and f3 to be the indicator function of this set A. Now, because A is very large, this right side will be a non-zero element. And from mixing, it will follow the left-hand side will also be non-zero. Okay, so we have the left-hand side to be non-zero, but if A was indeed product-free, then the left-hand side must be zero. So it follows that the subset A is actually not product free, because we know the left hand side is actually is non-zero, right? So this is the rough idea behind the argument. And certainly there are groups where we cannot hope to get any meaningful mixing result over the graph, over the hypergraph H1. For example, if G is abelian, then this kind of mixing will not be able to see, and simply because of the reason every abelian group actually has large product free or some free sets. So we cannot hope to get those kind of mixing for abelian groups. But there are certain groups, special kind of groups, for which mixing actually happens for H1. So in 2008, Gowers proved that mixing for H1 happens when the group G is d-quasi-random. Okay, specifically proved the following: if G is a finite d-quasi-random group, then the two terms we are concerned with, they are close to each other by this error factor 1 over square root of t. Okay, we haven't quite defined formally what d-quasi-random groups are. We'll do this later, but right now we just assume, okay, take d to be a very large integer. Then we can see if G is a d-quasi-random group, then we'll have a really good mixing for the hypergraph H1. So as d kind of goes to infinity, this error term we have over here goes to 0. And one point I'd like to note over here, so in this work, ours first defined the concept of quasi-random groups and initiated a study of such groups. Later, several results have been proven about this kind of groups, and some of which also found application in theoretical computer science. Okay, so let's continue our discussion, and let's focus on the other hypergraph now, which is the hypergraph H2. Here, again, just to recall, the H set is basically the set of all non-trivial progression, three-term progressions in G. So a mixing for the hypergraph H2 will actually imply any large A, any large subset A in G will not be three-term progression free. Okay, so and the argument is same as before that we just discussed. And Gowers, in the same paper from 2008, in the same paper where he defined what quasi-random groups are, he conjectured the mixing over the hypergraph H2 when the underlying group G is d-quasi-random. Okay, so here is the conjecture by Gowers. So let G be a finite d-quasi-random group, and again we pick the functions which are bounded ones. Then we compare these two terms. Then the absolute value of this difference is bounded by some little of one term. Now, this is the conjecture by Gowers for the hypergraph H2, and we'll refer to that is the conjecture on mixing of three-term progression. And our main result in this paper is we prove this conjecture for all d-quasi-random groups. Okay, so this is the precise result we prove in the paper. Let's take G to be a finite d-quasi-random group. Then we compare these two terms, where on the left-hand side, we sample X and Y randomly from G and construct the three-term progression X, XY, and XY squared and compute this expectation. On the right-hand side, we simply have the product of expectations, and these two quantities will be close to each other modulo this error term, which is 2 over square root of D taken to the power 1 by 4. So this is the main result in this paper that we proved. Now, let's try to formally define what the quasi-random groups are. And to do that, we have to define first what group representation are. So let's start with that. So here's the first definition. So our representation rho of a group G on a finite dimensional vector space V is simply a group homomorphism from the group G to the general linear group over the vector space V. Okay, so it's basically taking the group elements to invertible linear transformation over the vector space V. Now we use d rho to denote the dimension of a representation rho, which is simply the dimension of the underlying vector space V on which the representation rho is acting on. For us, all the vector spaces that we'll deal with will be over complex numbers. Here's an example of a representation, which is called the trivial representation. So if you take V to be the vector space of complex numbers, which is the one-dimensional vector space, then we can define rho x to be just one or, for all x in G. And this is called the trivial representation, and we can define it for any group G. From now onward, we'll just write rho, assuming there is some vector space V that is acting upon. So we'll keep that implicit. Here is another definition that will be useful to define what Quasirandom groups are. It's called irreducible representation. So first, let me define what reducible representation are. So a representation rho is called reducible if there exists a non-trivial subspace W of V or in V such that rho x, the linear transformation rho x applied to W keeps all the vectors within W, all the vectors from W. When you apply rho x on them, we keep them like within W. So rho x doesn't move the vectors within W outside of W. Okay, and this is true for all the x in G. So if this happens, then we call the representation rho is reducible. Otherwise, we call rho is irreducible. Okay, so this is the formal definition. Another kind of informal way to kind of think about them is a represented rho is called reducible if they can be further, broken into other representations. On the other hand, it's called irreducible if rho cannot be broken into further representation. Okay, so that's the idea behind irreducible representation. Here is a short note about notation. So G hat will denote the set, the finite and unique set of all irreducible representation. Unique in the sense like up to isomorphism. Okay. So before we move on, here's another example. So example of irreducible representation. So for the group G, symmetry group S3, there is a degree 2 irreducible representation rho that takes group elements to two-dimensional matrices, such as, for example, if we apply rho to the group element 1, 2, then it takes it to this matrix 1, 0, 0, minus 1. Similarly, it takes other group elements to other matrices. So that's one example. Now we can define what Quasirandom groups are. Okay, so what is the definition? So a finite group G is called D quasirandom if it's all non-trivial irreducible representations are at least d-dimensional. Okay, so that's the definition. Here are some examples. So abelian groups are one quasirandom. So we can readily see that Gauss's theorem about the hypergraph H1, mixing hypergraph H1, that doesn't say anything about abelian groups because it's one quasirandom, so you do not get any meaningful error bound. Okay, but there are other groups which are highly quasi-random. For example, if you consider the group SL2F, where F is the finite field, then there's going to be size of the finite field quasi-random. Okay? And if you take really, really large finite field, then it will be more and more quasi-random. Another kind of example is like if you consider any non-abelian finite simple group, meaning the groups which doesn't have any non-trivial normal subgroup, if you consider such groups of order n, then that will be square root of log n divided by 2 quasi-random. Okay, so if the group size increases, if it's really, really large, then it will be also very, very quasi-random. So now let's compare our result with known results in context of this conjecture. So Tao in 2013 proved this conjecture or showed mixing for three-term progression when the group G is SLDFQ. And for this, Tao used algebraic geometry machinery to prove the result. And then in 2018, Pelus extended the result to all finite simple groups. To do that, Pelus used kind of elementary Fourier techniques to reduce the problem to bounding a sum like this, where It is a sum of 1 over d rho, where rho belongs to G hat, which is the set of all irreducible representation, except rho cannot be the trivial one. So she reduced it to sum like this. And this quantity is equals to zeta G minus 1, where zeta G is the Witten zeta function of G. And zeta G minus 1 is small of or little o of 1 for all finite simple groups except for like except for one specific group PSL to F. This term is small, and this is a result. This is by a result due to Liebeck and Shalev from 2004, and Pelus uses this result to get the final bound on the finite simple groups. Okay, now we talk about our result. So we proved first of all, we proved the conjecture for all finite Quasirandom groups. More interestingly, the second point is our proof uses only elementary Fourier. And the third point is we also achieve better error parameter compared to Pelus. That's like the rough kind of comparison between our work and the previous works. Now let's talk about the proof of the theorem. So this is the theorem we are interested in proving, and which is equivalent to proving this statement. So these two theorems are almost same, except we over here we have this additional assumption that the expected value of the function f3 is 0. And that allows us to remove this product of expectation term. We can just get rid of it and work with a simpler looking term over here. And we can assume this without loss of generality because we can just shift the function if it's even if it's not mean 0. So that's fine. So we want to show this. And the proof is roughly divided into two main steps. Step 1 is repeated application of Cauchy-Schwarz and change of variables in order to reduce the problem into bounding a simpler term, which involves only f3 or the third function. Then in step 2, use basic Fourier to bound the term from step 1. So that's the overall structure. So let's briefly discuss how step 1 looks like. So step 1 is this. We use Cauchy-Schwarz and change of variables to show this quantity we start with is less than or equals to some quantity only involving f3. Here's an example step, how it goes. So this is the starting point over here. First, we do one change of variables. So previously we were doing sampling A and B, both from G, and setting this A, setting this pattern to be A, AB, and AB squared. Now we do a change of variable. We set we take AB to be X, and then also change B to Y. Then we have a new expression, same as the previous expression, both the same. So this is just a little algebraic manipulation. Then we do a Cauchy-Schwarz over X. This allows us to remove the function f2. So, okay, so we apply Cauchy-Schwarz and reach over here. Doesn't it have f2? Similarly, if we kind of do another Cauchy-Schwarz, we'll be able to remove f1 as well. So that's the rough idea behind step 1. And now that we are done with step 1, the problem roughly reduces to bounding a term like this, which is expected value of an L2 norm of a function like this. And this function is a convolution of two functions, this h function and the mu function, what these functions are. So hz of x is the mean zero of projection of this product function, which is f3 of x times f3 of xz. And to define mu function, so for any subset S in G, mu S is defined to be the indicator function of S up to normalization factor. And C of G is the conjugacy class of G. Okay, so this function is basically an indicator function of this subset G inverse C G inverse. And this function, H function, is the mean zero projection of this product function, which is a discrete analog of the derivative operator in some sense. Okay, so now that we are done with step 1, let's have a quick recap about where we are and how should we proceed from here. So we started with this initial term, applied a bunch of Cauchy-Schwarz and change of variables and some other algebraic manipulations to reach over here. So now we need to bound this. One quick note over here. So this step 1, which is repeated application of Cauchy-Schwarz, is is also there in Tao's proof as well as in Pelus's proof. So it's common to all of our work. And this technique was introduced by Gowers initially in the context of bounding expressions like this over abelian groups. Then Tao later in his work adapted the same technique in the non-abelian world. And Pelus and our work also uses the same steps. Okay, so now that we have successfully reduced the task to bounding a term like this, which only involves the function f3 inside it. Now the approach of Tao's, Pelus's, and ours kind of diverges from each other at this point. So on the left-hand side, this left arrow is kind of denoting Tao's approach. So Tao reduced the task to estimating quantities like YBH, where YBH is the coordinate of this set. We'll not discuss what this set is in detail. Rather, we'd like to point out Tao does this reduction as well as the estimation using algebraic geometric techniques, tools from algebraic geometry, including the very familiar Schwarzschild lemma. In the middle arrow, we have Pelus's approach, which we already discussed. Basically, she reduced the task to bounding sum like this, 1 over t rho. And this is bounded for finite simple groups because of the bound on Witten zeta function due to Liebeck and Saleh. Okay, now on the right hand side, this arrow is denoting our approach, which is basically using elementary Fourier analysis, and we'll discuss more on this. So before we go into slightly more details, let us recall some facts from non-abelian Fourier. These are all basic facts. So first of all, for any complex matrix, we'll the Hilbert-Schmidt norm of the Hilbert-Schmidt norm square of the matrix is simply the trace of this matrix product. So it's conjugate transpose of M times M itself. We take the trace of it and get the Hilbert-Schmidt norm square. And let's go over 4 very basic facts from non-abelian Fourier. So the first one is about the Fourier coefficient of f with respect to any representation rho. It is denoted by f hat of rho, and it is simply this expected value, this expectation of this fx rho x. So if rho is more than one dimensional, f hat of rho will be a matrix. Now let's talk about the Fourier inversion formula, which is fx equals to, again, sum over rho in g hat d rho times trace of this quantity, which is conjugate transpose of f rho times rho of x. The Parseval identity is also there in this non-abelian world. So L2 norm of f square is equals to the sum of the Hilbert-Schmidt norm square of f at rho multiplied by d rho. And finally, we have the Fourier convolution formula, which says the Fourier coefficient of the function f convolved with g at rho is equals to the Fourier coefficient of f times Fourier coefficient g. Along with this, we're going to use one more fact. So this function mu g cg, we already talked about. It has a very nice Fourier expression, and from that we can deduce that expected value of g of this quantity, that the Hilbert-Schmidt norm square of this inner quantity, this is equals to 1 over d rho. And this fact we'll use later in the proof, and this fact was also used by Sarah Pelus as well. Okay, now let's look at the proof. First of all, we abuse the notation a bit and write only mu cg instead of writing mu g inverse cg inverse. And let's start with the quantity that we had after step 1. So this is the quantity we had. The first and the most important observation over here is after we have sample g and fixed g, then we uniformly randomly sample b and look at the distributions on of G inverse BG, that will be also uniformly random over the group G. So what we can do, instead of computing the G inverse BG, ignore that completely. and just replace it with the B itself. Okay, so now that we have this, the next steps are quite easy. So we first use Parseval's identity to write this L2 norm as a sum of Hilbert-Schmidt norm. And then we use the Fourier convolution formula to separate out these two coefficients. And furthermore, we bring in, when they're separated out, we bring in another fact about Hilbert-Schmidt norm, which is Hilbert-Schmidt norm is known to be sum-multiplicative, meaning the norm of the product can be upper bounded by the product of the norms. So we use that to completely separate out these two Fourier coefficient. And also we bring in this averaging over G inside. Now we use the fact we discussed about the function mu CG. So this average is equals to 1 over d rho, and that d rho cancels this d rho. So now we are only left with this expression. Okay, so now we are basically done, because the expression we have over here, what you can do inside, we can multiply it and divide by d rho. Because d rho is at least uppercase T, we can take 1 by uppercase T outside, and this expression will be bounded by 1 by uppercase T times expectation of the sum times d rho times the Hilbert-Schmidt norm. And this is the L2 norm of the function HP, which is bounded by 1. So this expected value is at most 1. So we are done. This entire expression is bounded by 1 over d. So this was the rough sketch of the proof. Just to conclude, what we showed in this work is mixing of 3-term progressions for finite quasi-random groups. The next natural question is, of course, considering longer progressions, or like k-term progressions for arbitrary k. Another interesting direction could be possible applications in complexity theory. So we know applications of mixing in quasi-random groups in complexity theory, though for other kinds of patterns. And it would be interesting if we can find also applications for progressions as well. And this was the talk, and thank you for listening.